Okay, fundamental theorem, let's go. Wait, didn't we do this already? This is round 2. Here's this formulation. We're going to talk about the same things we did before, but we're just talking about it from a different angle. We're still talking about, the velocity versus position, that kind of thing. So in terms of our velocity position, this inside function, the small f, is our velocity, and the capital F is our position. So our accumulation of change, which is F, sometimes people use capital A, meaning accumulated change. And the way we draw this, and we've done this before, is we want to find, starting from some point A and going up to whatever point X you want, the area under the curve from f of x, little f of x, or f of t. Okay, so let's call it f of t so that this specific x here can be x. Okay, so we want to see that as x changes, as we pull this line, so I can do this a little bit on my computer. Here's x, but I want to make it like red. There we go. As I slide this along, it changes the area enclosed. Okay? We want to know how that is changing with respect to x. All right? So what we want to do is we want to do a derivative of this guy with respect to x. And you won't be shocked to know it's just f. We've been saying that all along. So I may as well just say that right out. It's just f of x. Well, so let's look at why that's happening. We did talk about this before, but it takes a while for these things to sink in. If you think about this little strip, this next, as I'm moving this along from x to x plus h, I'm creating a rectangle. And that rectangle, because h is very, very small, this rectangle is very much close to h times f of x. Okay? And so if I want to take the derivative of this guy, well, then what am I going to do? I'm going to say, okay, let me push these things around a little bit. Okay, so the most obvious thing to do if you want to take the derivative of capital F is just look at, first of all, I'm going to get rid of all this blue stuff so you can see what my definition of F was. Okay, so now I just evaluated at x plus h and at x, and clearly it's just this red rectangle. So now f prime is just the limit as h goes to 0 of that little strip, and we agreed that that little strip was h times f of x, and then the other h down here just comes from the definition of the derivative. So that's why f prime is equal to f. So it's kind of easier, I think, to see in this direction. But anyway, hopefully that makes sense. Now, there is a little bit of a problem because this is more than enough to get you through your worksheet, but it's not the whole story. There's one more step that you need to go through in order to get the full effect of this classic problem here. Is sometimes that instead of using an x up here, they'll use g of x just to make you mad. No, actually, we're going to end up using the chain rule. But no matter what, students always see that and choke. And so I'm going to show you how to deal with that because I think there might be a question like that on your web work. And if not, it's still just good for the soul. You've got to see this once. Okay, so here's what I want to do. I actually want to find df dx, but I'm going to split this into two different thought experiments. I'm going to say u is a new variable that's going to represent g of x, and actually I'm going to think of this in terms of f of u is like this. So I just replaced g of x with u, but I know that that means I got to put a u in here, and I'll deal with the other situation later. Okay? Now I know from the fundamental theorem df du is just f of u. Okay, so we know that much. But if u is g of x, we know du dx is just going to be the same as g prime, right? We're going to bring all this stuff together because what we really want is df dx, but what we have is df du, but we also have du dx, and by the chain rule we can put this all together, right? So df du, we have that du dx is just, okay, so df du is this guy, yeah, I'm just going to write df du as f of u, and I'm going to write du dx as g prime of x, but it's kind of sloppy because what is u? I know that u is g of x, so I write f of g of x times g prime of x. Okay, so I'm going to write this over here so that it's all together. So if I want to take the derivative of this stuff with respect to x, okay, that's going to be f of g of x times g prime of x. And then I don't care about this. Now I've got my theorem and everything works, and hopefully that all makes sense to you, because you're really just combining the fundamental theorem with the chain rule. But for whatever reason, every time you write a question like that or give students a question like that, they struggle with it. So it's better to just say, look, just look at, here's the way you do it. Here's how you solve it. If you run across it, it's not that bad now that you know that it's just another setup. So for example, if I say take the derivative of this guy. So what's f down here? I don't know, like sine of t dt, and we call this thing f of x. And somebody says to you, take the derivative of f, capital F, with respect to x, then what do? Okay, so try this one. Take some time and try it, and I'll put the answer up. Okay, so we just put all the pieces together. df, capital F, dx equals, now what do we see? You say f, so you don't have to take the derivative of sine, you just write it. And what's g of x is x squared, so you just dump it in there. And then you multiply by the derivative of g. Okay? Why do I love this? I love this because it looks really, really, really complicated, and it's not. It just looks complicated. So my favorite questions are the ones that look horribly complicated, and they're actually really easy to do. So this is why this is classified as one of my favorite problems. Okay? So hopefully you enjoyed that. And now I'm going to give you hints for this. So there's a couple questions on this worksheet 34 that have to do with the fundamental theorem, but then there's other things that you just need to review. So one hint that you need to review, I think we've talked about it before, but this lovely thing, x to the x, can be rewritten e to the natural log of x to the x, and then that means you can rewrite that as e x natural log of x. I'm pretty sure we've done this before, but that's an important hint. And then you're supposed to take the derivative of that. So you have a product rule inside a chain rule. And I'm pretty sure we did that. Maybe not, maybe not. Okay. Now, after that, there's something else I want to show you too. Okay, so there's a whole category of questions where you're finding the area bounded by some list of functions and lines. So you can have a function f and a function g, and the first thing you need to do is figure out where they cross. Okay, so maybe they cross at A, B, and C, and then they never cross again. Let's just say they never cross again, so that the only area bounded between these curves are as follows. You have to find the crossings, and then you have to say, okay, I'm going to integrate f minus g from A to B. And then you can, for example, from B to C, you can just flip that. So G minus F, and so on and so forth. So basically you just look at this geometrically. I do encourage you, if you're stuck, to go ahead and plot these online so that you get some additional intuition about these. There is a question in your worksheet. I'll let you find it, but you have some kind of function like this. I'm not really good at drawing this, I guess. And then there's another function like this, but they have exactly the same shape. So I wanted to draw your attention to this fact because you can make your life a lot easier for yourself if you notice the symmetry. If there's a symmetry here, and then you can just find a quarter of that and then multiply by 4 or something like that. Okay? So I just wanted to point that out, that there's often symmetries hiding in plain sight, and you want to take advantage of those, of course. And that is it for this worksheet. So if you've got everything I've said and you understand it and you've been able to do all the worksheets, that means you understand Calculus 1. Congratulations. And I will see you in class.